Hello, everyone. In this presentation, I'm going to talk about vectors and hidden patterns in geophysical data set collected as part of Metal Earth project, and look at the geophysical insights from differentially endowed terranes of superior craton. It's more than 2 decades that machine learning and recently deep learning has been extensively applied in mineral exploration, advancing exploration activities. Machine learning techniques like random forest, support vector machine, convolutional neural networks, and every day we are facing in new techniques. And they are trying to detect patterns inside the data set and so we can figure out which pattern can be related to any type of mineralization or target mineralization. For our case, the target mineralization is orogenic gold. We have data sets including gravity, magnetic data set, and magnetotelluric data set representing electrical conductivity. And also we have seismic data. Seismic data are not used in this study directly. Then we are trying to actually focus on them to reveal crustal structure and faults. And the target is superior craton, and comparing and contrasting 2 zones of interest in this study. The objective from this study is previous studies mainly applied supervised random forest for prospectivity or finding the probability of finding any orogenic gold mineralization. There are many published papers in the last 7 years, but this study we are trying to focus on unsupervised techniques to reveal hidden structures and patterns in geophysical data and related to orogenic gold mineralization. Well, geophysical variables highlight regional patterns. In Abitibi versus Wabigoon, we have targeted 2 terranes, less endowed and endowed subprovinces. And also we implemented a spatial analysis in order to find out the structures inside the geophysical data set, specifically magnetotelluric data and resistivity data set. Well, you're definitely familiar with this. We have a Abitibi in right-hand side and Wabigoon. We have selected 11 transects, 7 from Abitibi and 4 from Wabigoon, in order to analyze geophysical data and compare them together to see is there any contrast between the geophysical data set first, and secondly, find the hidden patterns in geophysical data that can help us in future for locating orogenic gold mineralization. This is an example of those 11 transects. We have a trace of magnetotelluric data collection on the surface. We have limited the boundary of geophysical data to 5 kilometers, 2.5 kilometers each side of the trace of the empty section, in order to make sure that we have an acceptable resolution and also accuracy of inversion modeling that is completed by geophysicists. So as we go further away from that, we lose the resolution or accuracy. So to be more confident, we have kept just that 5-kilometer boundary, and co-located density, susceptibility, and resistivity volumes, 15 layers from surface to minus 8,000 meters are collected, and those blocks are separated and actually inserted into the spreadsheets. And yeah, that's a 3D diagram of the Malartic transect. The data that we have used include density, susceptibility, resistivity. They are collected from GSC websites or Metal Earth Hub at Laurentian University. For the first 3 rows, we see the primary geophysical data set. And in the second part of the analysis, we have employed mineral potential mapping results from previous studies in the last 7 years that they have been published in different journals. And we collected those potential values, that were, in fact, the probability values over this 5-kilometer boundary in order to compare the unsupervised with supervised classification and try to interpret the geophysical patterns inside unsupervised classification. So the methodology we have employed, we use unsupervised clustering, CLARA, clustering large application. The extension of PAM stands for partitioning around midoids, which is applicable for large data sets. And we use midoid rather than mean because we are looking for robust results. And cluster multiple. In this technique, we cluster multiple random samples and selects the best solution to classify the samples and allocate each sample to each cluster. And in fact, before doing clustering, we have to define the number of clusters based on the criteria, and then we can apply any clustering technique that we have used Clara clustering in this study. Later, we have done correlation analysis between unsupervised and supervised clustering. We'll see the results later. And also, we have employed geostatistical techniques in order to identify spatial structural patterns in magnetotelluric data. For data preprocessing, we have log transform, resistivity, and magnetic susceptibility data to reduce skewness, and then we use robust scaling, interquartile scaling to normalize variables and get rid of some of those outliers. Well, outcome is enhanced clustering performance in noisy, heterogeneous geophysical datasets and accurate identification of inherent spatial and geological patterns. Well, how does Clara works is it's not just limited to Clara, but it's a general form. We are trying to minimize this cost function. We have a data we call it xi, is a data point. We have a midoid in this clustering technique for each cluster. We are trying to minimize the distance between or try to find the minimum distance between the samples and the midioid of the clusters. In this way, we're trying to allocate each sample to every cluster. In this case, as an example, I have just drawn this cartoon as a tree cluster, and we see the progress in the clustering. The first we have trees, we see that we have a bunch of data. In the first round, we allocate some samples into clusters, and then we can find the medians and try the next stage to minimize the cost function in order to allocate and label each of these samples to any of these clusters. That's how actually this clustering works. We have applied this Clara clustering as an unsupervised clustering in 3 different ways. The first approach was clustering all geophysical data all together. Well, we combined them. We combined magnetic susceptibility, density, and resistivity all together. We clustered them into 4 clusters. The criteria for 4 cluster was Silito plot. It's not here. Based on that Silito plot, I selected 4 clusters, and the clustering was completed. In order to compare the Abitibi and Wabigoon samples, I color-coded and plotted the box plot of each sample in each cluster. Well, if you look at magnetic susceptibility, there is no discernible pattern that shows differences between Abitibi and Wabigoon. The resistivity pattern is quite interesting. We see considerable low resistivities in all clusters for Abitibi compared to Wabigoon. And the other pattern is for cluster number 3 and cluster number 4, last 2 clusters, we see a clear separation between 2 clusters. Well, that was one of the objectives of the paper, actually this paper or research, that we want to see the differences. Again, for density, the pattern is mixed. Sometimes we don't see any difference between these 2 clusters, cluster number 1 and 2 and 3, but the last one shows very distinct separation between Wabigoon and Abitibi. The next approach was depth-wise clustering. We look at the similar depths of inverted models, and we collected all samples at the same level, and we clustered them with the same technique. We clustered them in considering 3 variables. And look at, again, we allocated number 4 to the number of clusters. The results are, again, quite interesting, that we see as we go down to deeper horizons, we see better separation between Abitibi and Wabigoon. And also, this happens more clearly in cluster number 3 and 4. If you look at here, we see that there is no sample in cluster number 3 and number 4 from Wabigoon, but we see a bunch of samples sitting in cluster number 3 and 4. And this is in horizon minus 6250. And again, we have this replicated here in the lower horizon, minus 7250. As we go further up and near to the surface, we don't see that much separation between the geophysical parameters near to the surface, and we can see that separation of Wabigoon and Abitibi. Well, here in fact, the idea was examine the vertical variation through the upper crust across all transects. The next analysis was clustering through unsupervised clustering, transect-wise. We look at just transects, and we collected the samples separately, labeling them inside each cluster, and we try to cluster them based on the similar clustering technique into the 4 clusters again. Everything is the same. If you look at you see this green color for Abitibi and orange color showing the transect from Wabigoon, 11 transects. This is one of the best output of actually this research, showing that if you look at the inside transect, we see there is a trend inside the clusters of each geophysical variables. In order to link between the supervised and unsupervised clustering, we collected probability values from previously studied MPM values based on that table that I showed you, near to 10, 11 papers we had on that. We collected all MPM values, which was related to gold mineralization. That was mainly done by random forest analysis. And we did not enter these values for clustering. We just used them to show the relation between MPM values and clustering values in 4 clusters. If we look at the MPM values, for example, for Shibugamo, we'll see an increasing trend from cluster number 1 to cluster number 4. This is replicated in density values. There's a similar terrain decreasing in resistivity, or if we invert it, we'll see an increasing trend similar to MPM value in conductivity. And there's a good correlation between MPM values and also magnetic susceptibility. Well, magnetic susceptibility is not the case always. We have seen less correlation between magnetic susceptibility and MPM values, but the output from this clustering is we see a good pattern and good agreement, high correlation between the MPM values and correlation between the density and resistivity in Abitibi. But it's not the case for Wabigoon. If you look at the pattern in MPM values of the Abitibi transects and the geophysical clusters in Wabigoon, we can see such a nice and high correlation values. In order to summarize that, I have calculated the correlation coefficient between MPM and 3 different geophysical parameters before clustering. I want to show how clustering can help us to classify and reveal hidden patterns of existing inside geophysical data. If we don't do any clustering, we see there is no high correlation, negative or positive, any of them. We can't see except that we can say it's a moderate high correlation between MPM and density, which is near to 70%, but the rest of the data without clustering, they do not show any discernible pattern that we can say, okay, we have found that this pattern related to orogenic gold mineralization appeared in geophysical data. But if now, this is the previous actually table that we have seen in the previous slide, that's the correlation analysis between the clusters of MPM and clusters of geophysical patterns after clustering. If you look at that, there's a dramatic changes and large number of high or low significant correlation values, which can be related to orogenic gold mineralization. And in fact, this reveals the pattern inside geophysical data set. That's one thing. The other thing is we have much more high correlation values between the geophysical parameters and MPM as a representative of orogenic gold in Abitibi and much less in Wabigoon. That's another difference. That's actually the target was to see the differences in addition to correlation between MPM and unsupervised. We want to see is there any differences between inside the geophysical features of Abitibi and Wabigoon, so we can see that here as well. For the next step, well, I was thinking if there is a correlation between resistivity and, well, we have seen that, we know from previous studies that there is a correlation between resistivity and faults. Well, how can we try to characterize faults or its proxy, actually? Its proxy is resistivity. In order to define the spatial characteristics and features inside geophysical data to see is there any differences between the fault patterns, especially, and to characterize them and contrast them to see is there any difference between Abitibi or Wabigoon. So I employed this formula from geostatistics, variography. Probably you're familiar with that. We can see autocorrelation or a spatial correlation between one variable in different locations. That's actually, this formula tries to find the correlation, or in fact variance, and we can calculate the correlation as well. At the end of the day, through this formula, we can calculate the variogram, and we can plot the variogram. And this variogram has three components. The type of variogram, all of them are, I calculated this variogram for 4 transects from Wabigoon and 4 transects from Abitibi. They have the similar model, all of them they have spherical. But there are 2 other parameters that characterizes each variogram. One of them is seal, or the maximum variance presented in each variogram, which is here. And the range of influence of each variable. That's another, actually, parameter. For the variogram, we can do it directionally in different directions. And if we do that, we'll see variation in these 2 parameters. All of them, they are presented as a spherical model. But the seal, the difference in the seal represents zonal anisotropy. And the difference in the range of influence, it presents geometric anisotropy. So if we have a zonal and a geometric anisotropy, we can look at these 2 parameters to see what's the difference between Abitibi and Wabigoon. Well, we can see it here through these plots, but I have plotted differently. We can easily see the differences. The brownish color shows seal value versus deep direction in different angles. I have plotted variogram and calculated the actual seal. And if we divide the maximum seal value to minimum, it shows the ratio for each seal and also for the range of the, geometric anisotropy and for zonal anisotropy. This brownish color shows the transect from Wabigoon, and this bluish color shows samples from Abitibi. Just visually looking at that, we see there is a big difference between the anisotropy or anisotropy ratio of Abitibi and Wabigoon. In fact, it represents it is based on electrical conductivity, and they are representing fault system, mainly fault system. It's not the only factor it's not the only contributing factors in the variance of the electrical data, but mainly we know that there is a correlation between faults and fractures and magnetotelluric data. So we have, in Wabigoon subprovince, we have a stronger anisotropy overall. Dryden shows the highest geometric anisotropy. The ratio is 3.24, and the zonal anisotropy is equal to 5.18. Joalton Sturgeon moderate anisotropy, and Rainy River is similar to Abitibi. We know in other features, Rainy River is showing similar behavior, similar geology to Abitibi, and even in the anisotropy analysis, we see that Rainy River is showing weak anisotropy, which is quite similar to the Abitibi. In Abitibi subprovince, generally we have lower anisotropy, more isotropic resistivity structures, Larder Lake, Malartic, and Matheson, minimal directional influence. And for Chibougamau, we have the highest anisotropy amongst Abitibi transects, 2.37 for range, and 1.8 is for the seal. Well, when we saw this pattern, we tried to see, is there any correlation between the faults and this zonal and geometric anisotropy that exists, and the differences that we saw between Abitibi and Wabigoon? So we selected based on data availability and the quality of data. We selected 4 transects, 2 from Abitibi, Malartic and Noranda, and 2 transects from Wabigoon, Dryden and Rainy River. And we calculated the fault density based on the length of fault and the area of covered area. And we see, yes, we see that pattern here replicated. We see very high number, very large number of fault density in Abitibi in these 2 transects, near to 6 and 6.8 for Malartic and Noranda, respectively, and much less fault density for Rainy River is 3, and for Dryden is 2.29. Well, they are all supporting each other. They are telling the same story, that we have more homogeneous. This can be a reason to more homogeneity in Abitibi. That's one reason. The other reason can be pervasive alteration, maybe. But this part of the story supports the homogeneity that we saw in variography and less homogeneous segmented structure in Wabigoon. This table shows the essence, and actually is a key table which can be used to show the hidden pattern inside the dataset. If we have dataset from 3D, if we collected 3 parameters, measured 3 geophysical parameters, and we did the same thing in different part of Abitibi or Wabigoon, we can do similar clustering, and we can use this table. Definitely it can be improved or modified, but we can use this table to show the hidden structures and to locate the potential areas for orogenic gold mineralization through unsupervised clustering, because for supervised, we know we have to have locations of mines or prospects or mineralization, but in unsupervised, we don't need any of them. So we can do similar thing, and we can look at this key table and try to interpret other, our information that are collected from unknown study. We have classified based on high density zones, deep horizons, fault density, susceptibility, near surface conductive anomalies. These are the features that are seen which can show us the relation between orogenic gold and these 4 variables. Actually, if we have seismic, if we don't have it, we have to look at just 3 variables. And just to show as an example of this table, we see that on top 3D model of the Malartic, and below we see that Rainy River. All of those patterns can be seen as an example here for in Malartic representing Abitibi and Rainy River representing Wabigoon. This surface, the top map shows the MPM values formerly completed, and we see the hot and red points showing the higher probability for orogenic gold, and the blue one showing lower probability for orogenic gold. We see where we have a high probability for gold. We see high density in deeper horizons. This is summarized in the table. And the middle one shows resistivity. Usually we see good correlation, not very perfect correlation between resistivity and gold. And as I said, there is no clear pattern between magnetic susceptibility and gold potential. And below this one is showing actually the relation between the sample from Wabigoon and these 4 parameters, MPM and 3 other geophysical data set. Again, we see this appeared again. We have high density in deeper horizons in Wabigoon as well, when we have a high potential of gold favorability map. And yeah, that's again summary of the previous things. Yeah, that's it.